The first known prosthetic was from 500 BC and was just a simple wooden stub. Later the stub was refined to more closely resemble a human arm. However, it was not until just before World War II when the first mechanical prosthetic was developed. This prosthetic allowed the user to grip things between two metal rods by shrugging their shoulder, but it could not replace the limb lost. Today, with the advancement of modern technology, robotic arms can accurately mimic fluid human motion. However, the user had previously no realistic way of controlling their arm. Thankfully, recent advancements in electromyographic technology are allowing users to control their arm like never before. With such a prosthetic, amputees are finally independent in their activities of daily living. In order to understand how electromyographic control systems work, we must first understand how the brain controls muscles and how this creates electromyographic signals. First, the frontal lobe of your brain decides that you'd like to flex your wrist. Your frontal lobe then sends a signal to your cerebellum that sends an action potential or neural signal through your nervous system and finally into the muscle itself. The action potential is then distributed along the muscle by the scaroplastic rectilium so that the muscle fibers simultaneously contract. This works by releasing calcium ions into the muscle. These ions expose the binding sites along the entire muscle and allow cross bridges to attach between the muscle fibers. These cross bridges pull the fibers together, contracting the muscle. This process repeats multiple times until the muscle is tense and continues to pulse until the nerves are no longer transmitting an action potential from the brain to the muscle. Now that we understand how myoelectric signals are produced, we need to take a look at how they are detected and interpreted. The calcium ions released to facilitate the contraction produce a minute amount of electricity called a myoelectric signal. Because the calcium ions are released simultaneously, their myoelectric charges combine and produce a myoelectric signal that is strong enough to reach the surface of the skin. In order to detect these signals, a myoelectric sensor is placed on the surface of the skin where the myoelectric signal is the strongest, often called myoelectric sites. Placing the sensor in these areas is key in accurately determining the user's intent because they are less susceptible to interference from other muscles and more sensitive to the target muscle. Traditionally, myoelectric prosthetics had only one function, opening and closing. However, with today's advanced manufacturing and engineering abilities, modern electromyographically controlled prosthetics can perform many complex motions, similar to the human hand. For instance, DARPA's prosthetic arm can rotate in 27 independent ways, and allows it to accurately mimic human motion. However, using traditional electromyographic control systems, the user has no practical way of controlling the 27 different degrees of freedom, even with multiple myoelectric arrays. Now, with modern control systems, the sensor data can be interpreted cleverly to allow complex hand functions. For instance, Touch Bionics has developed a smart control system that utilizes different user-specific modes to facilitate advanced control of their prosthetic. For example, if the user sends a long open signal and then pulses their muscle twice, the hand could go into a pinch grip mode and allow the user precise control of the index finger.